In mathematical group theory, given the prime number p, a p-group is a group in which each element has a power of p as its order. That is, for each element g of a p-group, there exists a non-negative integer n such that the product of pn copies of g, and not less, is equal to the identity element. The orders of different elements may be different powers of p. Such groups are also called p-primary or simply primary. A finite group is a p-group if and only if its order is a power of p. Given a finite group G, the Solow theorems guarantee for every prime power Pn that divides the order of G the existence of a subgroup of G of order Pn. The remainder of this article deals with finite p-groups. For an example of an infinite abelian p-group, see proof a group, and for an example of an infinite simple p-group, see Tashi monster group. Properties. Every p-group is periodic since by definition every element has finite order. Non-trivial center. One of the first standard results using the class equation is that the center of a non-trivial finite p-group cannot be the trivial subgroup. This forms the basis for many inductive methods in p-groups. For instance, the normalizer n of a proper subgroup H of a finite p-group G properly contains H, because for any counterexample with H equals n, the center Z is contained in n, and so also in H. But then there is a smaller example H, Z whose normalizer in G, Z is n, Z equals H, Z, creating an infinite descent. As a corollary, every finite p-group is nilpotent. In another direction, every normal subgroup of a finite p-group intersects the center non-trivially, as may be proved by considering the elements of n which are fixed when G acts on n by conjugation. Since every central subgroup is normal, it follows that every minimal normal subgroup of a finite p-group is central and has order p. Indeed, the cycli of a finite p-group is the subgroup of the center consisting of the central elements of order p. If G is a p-group, then so is G, Z, and so it too has a non-trivial center. The preimage in G of the center of G, Z is called the second center, and these groups begin the upper central series. Generalizing the earlier comments about the cycli, a finite p-group with order Pn contains normal subgroups of order pi with 0 in, and any normal subgroup of order pi is contained in the ith center Z. If a normal subgroup is not contained in Z, then its intersection with Z plus 1 has size at least pi plus 1. Automorphisms. The automorphism groups of p-groups are well studied. Just as every finite p-group has a non-trivial center so that the inner automorphism group is a proper quotient of the group, every finite p-group has a non-trivial outer automorphism group. Every automorphism of G induces an automorphism on G, phi, where phi is the Fratini subgroup of G. The quotient G, phi is an elementary abelian group and its automorphism group is a general linear group, so very well understood. The map from the automorphism group of G into this general linear group has been studied by Burnside, who showed that the kernel of this map is a p-group. Examples. P-groups of the same order are not necessarily isomorphic. For example, the cyclic group C4 and the Klein 4 group 5-4 are both two groups of order 4, but they are not isomorphic. Nor need a p-group be abelian. The dihedral group DIH4 of order 8 is a non-abelian 2 group. However, every group of order p2 is abelian. The dihedral groups are both very similar to and very dissimilar from the quaternion groups and the semi-dihedral groups. Together the dihedral, semi-dihedral, and quaternion groups form the two groups of maximal class. That is, those groups of order 2n plus 1 and nilpotency class n. Iterated wreath products. The iterated wreath products of cyclic groups of order p are very important examples of p-groups. Denote the cyclic group of order p as W, and the wreath product of W with W as W. Then W is the Solow p subgroup of the symmetric group Sim. Maximal p subgroups of the general linear group GL are direct products of various W. It has order pk where k equals It has nilpotency class Pn-1, and its lower central series, upper central series, lower exponent P central series, and upper exponent P central series are equal. It is generated by its elements of order P, but its exponent is Pn. The second such group, W, is also a p-group of maximal class, since it has order P plus 1 and nilpotency class P, but is not a regular p-group. Since groups of order pp are always regular groups, it is also a minimal such example. Generalized dihedral groups when p equals 2 and n equals 2. W is the dihedral group of order 8. So in some sense W provides an analog for the dihedral group for all primes p when n equals 2. However, for higher n the analogy becomes strained. There is a different family of examples that more closely mimics the dihedral groups of order 2n, but that requires a bit more setup. Let zeta denote a primitive pth root of unity in the complex numbers. Let z, zeta, be the ring of cyclotomic integers generated by it, and let p be the prime ideal generated by 1 minus zeta. Let G be a cyclic group of order p generated by an element z. Form the semi-direct product E of z, zeta, and G where z acts as multiplication by zeta. The powers Pn are normal subgroups of E, and the example groups are E equals E, Pn. E has order Pn plus 1 and nilpotency class n, so is a p-group of maximal class. When p equals 2, E is the dihedral group of order 2n. When p is odd, both W and E are irregular groups of maximal class and order pp plus 1, but are not isomorphic. Unite triangular matrix groups. The Solow subgroups are general linear groups are another fundamental family of examples. Let V be a vector space of dimension n with basis E1, E2, n, and define Vi to be the vector space generated by A plus 1, n, for 1 in, and define Vi equals 0 when I greater than n. For each 1 mn, the set of invertible linear transformations of E which take each Vi to Vi plus m form a subgroup of AUT denoted If V is a vector space over Z, Pz, then U1 is a Solow P subgroup of AUT equals GL, and the terms of its lower central series are just the In terms of matrices, are those upper triangular matrices with 1s1 the diagonal and 0s on the first m-1 superdiagonals. The group U1 has order Pn, 2, nilpotency class n, and exponent pk where k is the least integer at least as large as the base p logarithm of n. Classification. The groups of order Pn for 0 and 4 were classified early in the history of group theory, and modern work has extended these classifications to groups whose order divides P7. Though the sheer number of families of such groups grows so quickly that further classifications along these lines are judged difficult for the human mind to comprehend. For example, Marshall Holt Jr. and James K. Sr. classified groups of order 2n for N6 in 1964, rather than classify the groups by order. Philip Hall proposed using a notion of isoclinism of groups which gathered finite p-groups into families based on large quotient and subgroups. An entirely different method classifies finite p-groups by their coclass, that is, the difference between their composition length and the nilpotency class. The so-called coclass conjectures describe the set of all finite p-groups of fixed coclass as perturbations of finitely many pro-p-groups. The coclass conjectures were proven in the 1980s using techniques related to Lie algebras and powerful p-groups. The final proofs of the coclass theorems are due to A. Shalev and independently to C. R. Leadham-Green, both in 1994. They admit a classification of finite p-groups in directed coclass graphs consisting of only finitely many coclass trees whose members are characterized by finitely many parametrized presentations. Every group of order P5 is metabelian. Up to P3 the trivial group is the only group of order 1, and the cyclic group CP is the only group of order P. There are exactly two groups of order P2, both abelian, namely CP2 and CP times CP. For example, the cyclic group C4 and the Klein 4 group 5-4, which is C2 times C2, are both two groups of order 4. There are three abelian groups of order P3, namely CP3, CP2 times CP, and CP times CP times CP. There are also two non-abelian groups. For P2, one is a semi-direct product of CP times CP with CP, and the other is a semi-direct product of CP2 with CP. The first one can be described in other terms as group UT of unite triangular matrices over finite field with P elements, also called the Heisenberg group mod P. For P equals 2, the both semi-direct products mentioned above are isomorphic to the dihedral group DIH4 of order 8. The other non-abelian group of order 8 is the quaternion group Q8. Prevalence. Among groups, the number of isomorphism classes of groups of order Pn grows, and these are dominated by the classes that are two-step nilpotent. Because of this rapid growth, there is a folklore conjecture asserting that almost all finite groups are two groups. The fraction of isomorphism classes of two groups among isomorphism classes of groups of order at most n is thought to tend to 1 as n tends to infinity. For instance, of the 49,910,529,484 different groups of order at most 2,000, 49,487,365,422, or just over 99%, are two groups of order 1024. Within a group, every finite group whose order is divisible by P contains a subgroup which is a non-trivial P group, namely a cyclic group of order P generated by an element of order P obtained from Cauchy's theorem. In fact, it contains a P group of maximal possible order. If where P does not divide M, then G has a subgroup P of order called a solo P subgroup. This subgroup need not be unique, but any subgroups of this order are conjugate, and any P subgroup of G is contained in a solo P subgroup. This and other properties are proved in the Solow theorems. Application to structure of a group. P groups are fundamental tools in understanding the structure of groups and in the classification of finite simple groups. P groups arise both as subgroups and as quotient groups. As subgroups, for a given prime P1 has the solo P subgroups P and the P core, and various others. As quotients, the largest P group quotient is the quotient of G by the P residual subgroup. These groups are related, possess important properties such as the focal subgroup theorem, and allow one to determine many aspects of the structure of the group. Local control. Much of the structure of a finite group is carried in the structure of its so-called local subgroups, the normalizers of non-identity P subgroups. The large elementary abelian subgroups of a finite group exert control over the group. That was used in the proof of the Veit-Thompson theorem. Certain central extensions of elementary abelian groups called extra-special groups help describe the structure of groups as acting on symplectic vector spaces. Brouwer classified all groups whose solo two subgroups are the direct products of two cyclic groups of order 4, and Walter, Gorenstein, Bender, Suzuki, Glaberman, and others classified those simple groups whose solo two subgroups were abelian, dihedral, semi-dihedral, or quaternion.